16 cubes, right? Total. We had an orange cup and then 2 blue, right? And then 3 of another color. We'll go with red.
Pink.
Pink? Okay. Yes. So, how do you solve a problem like Maria? Bo.
I just had ones in all of them except for the top, and on the top I had 11.
Okay.
Because I gotta have all the same color has to have the same color.
So that's 5, right?
Yeah.
And you need 11 here, which is kind of cool looking, right? It's all ones. So Bailey asked a good question. Is there only one solution, or are there infinitely many? What do you think? Infinitely many, or at least a bunch if we're assuming whole numbers, right? Yeah. Zed.
All 3s except the top ones.
Right. So if we're allowed to have blue equal pink, right, or have different colors equal each other, like in this case, that opens up a lot more possibilities. So what if we said that blue and pink had to be different numbers, right? Pink can be its own thing, blue has to be its own thing. Cheyenne. So we had 3, 2, and 6. Yeah, Shelby.
I did 4 in the bottom ones, and then I did 2 in the blue ones, and I did 0 in the top ones.
Ooh, interesting, right? If we're allowed to use 0, right? Yeah.
I did 2 in the pinks, 1 in the blue, and 8 in the orange.
Right. So this problem is fairly trivial, right? And the reason for that, I think, is a couple things. One, this top one is really just where you dump all your rest of your cubes, right? You do whatever you want down here, and then whatever's left over, you throw it in here. If I gave you 17 instead of 16, you could have done the exact same numbers you had here, and then just threw an extra one up here, right? So the problem becomes pretty trivial, considering that this guy's just where you end up dumping all of your stuff. Do I want to extend this today, or do I want to cut you guys loose? Since I think we want to cut you guys loose today, and then we'll hit this more tomorrow because we're a little bit behind in first hour. But just a little bit of extension. So what we have here is 3 times x, basically, if you're thinking algebraically, plus 2 times another number, let's use y, plus z has to equal 16. So from looking at this algebraically, you should see that there are going to be infinitely many solutions. If we limit our answers like this, that x, y, and z exist in the natural number set, right? Or let's do whole numbers, so 0 is included, right? And then there won't be infinitely many solutions, but there will be a lot, right? Infinite means we can have like halves, quarters, etc., right? There's going to be infinitely many numbers there. But the numbers between 0 and 16, obviously there's only so many numbers you can check and different combinations that you can do. So it won't be infinite, it would be a lot. For this problem, since we're talking about cubes, it's probably a good idea that we do limit those numbers to be within the natural or the whole number set, right? You're not going to have a half a cube under any of these. 0, potentially possible. But when we have one equation with 3 different variables, it'll always have infinitely many solutions unless we limit it some other way, right? If we have an equation with one variable, like 2x equals 4, how many solutions will that have?
1.
Just one, right? X equals 2.
So you are saying that they can't be the same repeated numbers because they're different?
We could make that rule, or we could allow x to equal y, right? That's what some people did. They did 1, 1, 1, 1, 1, right? That was
Because
Bo.
I did 8 for blue and then 0 for the red.
Right, you could have done that as well, right? So if x and y can be equal, or y and z can be equal, or something like that, right, it opens up a lot more possibilities. But just with one variable, we get one solution, guaranteed every single time. Generally, the rule is that if you have more variables than you have restrictions, then you're going to have infinitely many solutions. If you have the same number of variables as restrictions, then you're going to have one solution. So this equation right here represents a restriction, right? What does x have to be? Well, it has to be a number that when you multiply it, it gets 4, right? So one restriction with one variable, only one answer. But if we have one restriction whatever this guy is times 3 plus this guy times 2 plus this guy has to be 16. That's one restriction, right? But we have 3 different variables to play around with. We're going to have multiple answers, which is why when you had algebra last year and you had stuff like this, this was solvable, right? If both of these were included as restrictions or equations, right? You could solve for x and y because there's 2 variables and there's 2 restrictions or 2 equations. And you get one specific answer. Now, sometimes these would represent lines that are parallel, which means they'd have no solution because they never intersect. Or maybe they would intersect at exactly one point and we get that one solution that we were talking about. Or maybe they'd be the exact same line and they'd have infinitely many solutions because of that. But in general, when you have 2 equations, you're generally going to expect something like this. And that makes sense because geometrically, when you have lines, there's 3 options, right? They're askew, meaning they hit at some point. They're parallel, they don't intersect at all. Or they're the same line and they intersect constantly, right? So when you have 2 lines, the odds of them being the exact same line, right? If I just draw 2 random lines in there and have them be the exact same line, pretty rare. Draw 2 random lines, right? Having them be perfectly parallel, pretty rare. Most lines intersect at one point, which is why when we have 2 lines like this, we would expect one answer. So the number of variables and the number of solutions when they match is going to be the number of answers that you get, right? It's going to make it 1. But if you have more variables than restrictions, then you're going to have infinitely many, which is what we have here, right? We've got 3 different variables, pink, blue, and orange, and we only have 1 restriction, right? They have to add up to 16. So if you wanted to make this problem more specific, you could say something like, these have to be even, and maybe these have to be odd. And then maybe, that's 3 restrictions, right? 16, odd, and even. And then you should have 1 specific answer for this, in theory. Does anybody know what the answer would be if these have to be even, these have to be odd? Yeah, give me an answer. Can anybody think of another answer? Yeah. Yep. So there are multiple solutions for this one, even with these 3 restrictions. Because what we have here is that x is even, and we have that y is odd. But do we have any restriction on z? No. So there's no restriction for this guy other than that whatever it is has to add up to 16. So if we had another restriction here, maybe we could make it where it has 1 specific answer. We're going to play around with that a bit tomorrow, playing with different fields of numbers. Put that away for now. All right, so I believe we left off. I can't remember because my voice was really bad on Friday, and I was very tired. But I believe we did page 7. Did we prove this? Yes or no? We did not? Okay, awesome. So everybody else did. We need to catch you guys up. So the one before that is just saying the theorem. So if you want to take a look at 6, we can, but I'm going to go to 7 really quickly. They look really similar because one is proving the theorem and one's just stating it. Sorry, I wasted a whole page doing that. So the angle bisector theorem. Don't call it that. Call it the triangle angle bisector theorem. The angle bisector theorem states this, that if you have an angle and you bisect it, that means any point on that line on the angle bisector will be the same distance from both sides of the bisector. Yikes. Yeah, stop doing that. They're really expensive. $25 every time I buy a new set. It's okay. Not these ones. These aren't that expensive. All right, so regular angle bisector theorem, not triangle angle bisector theorem, says this, and we haven't really learned this, but I think you can prove it true. If you have an angle that's bisected, right, if we're given this, then we know that point will be the same distance from both sides. And the reason for that is because if you were to draw a line from both sides at 90 degrees, right, and that's how we measure distance, then we would have a shared side here, right, and now we've got hypotenuse leg. So that would mean these 2 are the same.
Which one is that?
We're on number 6. So this is regular angle bisector theorem. What we're talking about is angle bisectors in a triangle. So call that the triangle angle bisector theorem. My bad. There have been some mistakes in this packet, and I apologize for that. So it says if this is an angle bisector, right, then these 2 sides of the angle will be proportional to the bases. here and here, which is kind of crazy because no matter how you try, you're never going to get that these two triangles are similar. You're never going to be able to prove that. So we're not going to get this through similarity. We have to do a little outside the box. So how do we prove this and prove it's true? And we need this to be able to prove that angle bisectors are always concurrent. So here's what we're going to do. Take out my ruler. We're going to draw a parallel line, a line that's parallel to the one of the sides of our angle, right? This angle that's been bisected. So I can draw a parallel line to here, right? Down here somewhere. Or I can draw a parallel line to this guy. I'm going to draw a parallel line to this guy. Doesn't matter which one. But I'm going to do that because I don't have enough triangles to prove this, so I'm going to add one more by drawing a parallel line. So we're going to call that parallel. So a little symbol here, here. And let's call that CQ. And then we're going to extend this guy. So we're going to extend the angle bisector. Nice. All right, so, and we're going to call the point of intersection X. Why not? So in order to state that for our proof, we're going to say let's do that in blue, let CXQ exist, and let ADX exist. Now remember, when two line segments share a point, that means they intersect there, right? So where do ADX and CXQ intersect? Well, at the point they share, right? They're going to intersect at X. So that's why I wrote that. And if you notice, after doing that, I've got another triangle. Don't forget that we're given that AD bisects BAC, right? Which means these two angles are congruent. We're given that. Were those two angles enough to get the job done to prove these similar? No. In fact, you're not going to be able to prove them similar unless this is a 90-degree angle. And if that's the case, then the triangles will be congruent. But we're not given that that's 90, so we can't do that. So what I did is I added on another triangle. That's going to help me prove this thing. Because I'm going to get one of these two triangles similar to this guy. What do you see? We've got parallel lines, right? So what should you be looking for? Corresponding angles, alternate interior angles, stuff like that. What do you see? Ooh, sorry. I will lower my head. Cheyenne. Alternate exterior angles. Interior? Okay, what do you see?
Angle CAD should be congruent to CXD.
So CAD is this one, right? So she's talking about this one. And then CXD, these two. They will be congruent, but it's not because CAD is congruent to this guy, because they're not alternate interior. They're both on the same side of the transversal here, right? We have two parallels, and here's the transversal, right? So they're on the same side, so that wouldn't be a thing. Do you know what angle is alternate with it, though? Yes, this angle here. So guys, this angle right here, and both are congruent, but it's important when you're talking about this to actually use the one that's alternate. Remember, alternate means opposite sides of the transversal, right? These guys are on opposite sides of their transversal, and they're inside the parallel, so it's alternate interior. These two are congruent. Bailey, what else do you see? Yep. So I'm going to do this first, and then we'll get to that. By alternate interior angles theorem, angle DAB, don't you dare, is congruent to angle CXD. Looks like a happening dude. Look how happy he is. His cool hair. All right. So, and then Bailey said, vertical angles. Where do you see vertical angles? Yep. So all of these two and these two are vertical because they're x's, right? I'm going to highlight this one and this one as vertical because this guy isn't a triangle. We could connect and draw another triangle, but again, we got enough to get the job done. So by vertical angles theorem, angle CDX is congruent to angle ADB. Awesome. So which triangles are going to be similar? Shelby?
Top and bottom.
Yeah, these two, right? They're going to be similar. How do we know that they're similar? By angle, angle, right? They both have red and they both have green. So by angle, angle, those two triangles are similar. I'm going to zoom out. By angle, angle, similarity. Triangle, I'm going to go with ABD here. So you've got ABD. Angle A is going to go with what in this triangle? X. And B, the unknown angle, must go with C. And then D is going to go with itself. Typically, when you have vertical angles, that's how that goes. So they're similar. And now we can start talking about their parts. So again, our goal is to get X and Y together and A and B together. And if you look for these two triangles, well, doesn't this triangle have side A in it? Right? And this bottom triangle has side B. So we can get A and B by CSP. So that's good. But notice this guy has Y, but this guy does not have X. So we're not going to get X and Y from this unless we can prove that these two triangles are connected somehow. I'm going to give you a second to look. What do you see? Linear pair? Where do you see a linear pair? Like here and here? That's true. So this right here will be the same as this right here. That's not going to be helpful, so I'm not going to write it down, but it's definitely true. These two angles are going to be the same. What do you notice? What else do you notice? I'm just trying to streamline it for today, but if you were doing this on your own, you could definitely write that down. Bailey, what do you see? This whole thing? Yeah, it could be because this is a straight line, right? We just extended it. So that'd be a triangle. Yeah, Cheyenne?
They're shared side.
What do you mean?
Triangle CAD and triangle CXD both share the side A.
CAD and CXD. Okay, so I'm not going to call it a shared side. So an example of a shared side would be the side between these two triangles, right? They literally share it. Does that make sense? What you mean is there's a congruent side. These two are, right? That's what you meant. Now, I'm going to write that down. And Cheyenne, you don't tell me because I know you know. How does she know that these two sides are congruent? Yes! Isosceles triangle theorem. Do you see it?
No.
Look at triangle CAX. So is it the theorem or the converse? Which one? Converse, right? Because we have the angles, we get the sides. So by isosceles triangle theorem converse, right, these two sides must be the same. Very proud of you guys. Well done. We know that AC is congruent to XC, which implies that XC equals little x, right? Algebraic x, little guy. Ta-da! And so now that we know these are similar, we can do CSP and we're going to get the things we want, right? So, by CSP, let's match stuff up. AB, XC, am I in your way somehow? Or no? Yeah. Should I raise this up? You raise me up. Which then implies, let's fill in little letters now, because that's what we want, right? So AB, little y, XC is algebraic x, little x. BD is little b. CD is little a. And then yada, 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 I don't care. Because look, I've got what I want, right? Now what do I have to do to get that to match what I'm trying to prove? Flip them both, right? Therefore, x over y equals a over b. So the relationship between these two sides will be the same as the relationship as the basis here. It's kind of cool. Unless you're playing around with the math and drawing extra triangles on, it would be weird to prove that, right? Because these two triangles are not similar. Let's far as we know. So we had to draw on this extra guy. Cool. So, how do you feel about that? Weird that we have to draw on an extra thing, right? But I think you guys kind of led me through this, right? You saw these two here. You could have also said that, let me grab a different color, let's go orange, that these two angles are alternate interior. You guys see how they're alternate interior? This would be the transversal, right? Alternate sides, interior of the parallels. So you could have gotten those two together instead of getting the vertical. And then you could have gone angle, angle, right? It's up to you. But this is the big one that you gotta see. Are you feeling okay with that? Alternate interior, vertical angles, whatever you want. These get similar. And then the big catch is that this is an isosceles triangle. So good job, Courtney. And now that these two are both x, I can get x and y and a and b together. How you feel? All right, well, we're going to use this theorem, the triangle angle bisector theorem, that says sides of the angle that you're bisecting are proportional to the bases. We're going to use that to prove that angle bisectors have to be concurrent. So turn the page. Numeral 8. Does everybody have the new copy of this that has X, Y, and Z and G in the middle instead of D? And it doesn't just say AD a bunch of times?
Wait, what?
Does yours say AD a bunch of times over here? Good. Then you have the new copy.
Wait, what? Mine has 2 Y's on the side.
Okay, yep, then you have the old copy, so let me get you the new
I
one.
have a new one, I thought.
Maybe you did, but you didn't replace it.
Is it this one?
Yes. So replace the old one with that. Somehow, some way. It's on the back of something, so you might just have it crossed out. All right, so my document saved in the middle of it, which is good, because then when my computer crashed and I reloaded it, it looked like everything had saved automatically, but it actually saved in the middle of me making this problem. So the template was left over. But the rest of you got the good stuff. All right, so we're going to prove that the angle bisectors of a triangle are always concurrent. So I gave you a triangle, and I told you that these are angle bisectors, A, E, B, F, and C, D, right? And we're going to prove that they're concurrent. Now, if we know they're angle bisectors, then angle bisectors theorem is good to go, right? We can use that, triangle angle bisector theorem, which we just learned. So focus on bisector CD, right? We know that's an angle bisector, so that means we get this and this for free, right? I'll zoom in. And since AE is an angle bisector, we get this and this for free. If you're not using color, use double bands, right? And BF is also an angle bisector, so we get this for free. Right? Cool. And we're going to prove they all do intersect at a point G. All right, so let's focus first on CD. It's an angle bisector. So by triangle angle bisector theorem, x over y should equal a over b. Isn't that what we proved in the last one, right? If we have an angle bisector, then the sides of the angle that we're bisecting will be proportional to the bases, right? So x over y equals a over b. We cool with that? All right, so I'm going to write that. By triangle angle bisector theorem. I don't know how you want to abbreviate that. You could probably draw a triangle like this. That's a triangle angle bisector, right? Triangle angle bisector theorem. We know that x over y equals a over b. So that's cool. And can't we do by the same dumb logic with everything else, right? So we know x over y, a over b. AE is an angle bisector, right? So look at the letters that we use for our angle, right? Z and X, right? Aren't those the sides of the angle we bisected, right? So Z over X should equal C over D. Does everybody see that? I'm bisecting this angle, right? So Z and X are the sides of that angle, and they go with the bases, C and D. All right, last angle bisector, this guy over here, BF. What are the sides of the angle that I'm bisecting? What little letters are those? So I'm bisecting this angle. What are the sides of those angles, the little letters?
BC. Wait, what?
So those are the big letters, right? BC is one side of the angle, and BA, right? What are the little letters for those? Ooh, don't, a D plus C would be that, right?
Yeah.
Keep it simpler. What are the little letters? Y and Z. I asked the questions. Yes, YZ. So YZ must equal EF. So I'll highlight this again. If you haven't been seeing it, go back to the first one. CD, angle bisector, right? What angle is it bisecting? This angle, right? What are the sides of those angles? X and Y. The sides of the angles should go with the bases, A, B. We cool with that? Zed, you with me? All right. Cheyenne? All right. I did that for all of them. Cool. So, if I can prove that A over B times C over D times E over F equals 1, don't write this down, but if I can prove that, then we can use Ceva's theorem's converse to prove they're concurrent, right? Right? If this is true, then they must be concurrent. That's Ceva's theorem's converse. So, how can I prove that A over B times C over D times E over F equals 1? Well, what I can do is I can just write A over B times C over D times E over F and figure out what they equal. Don't I know what A over B is, right? It's X over Y. Times, what's C over D? C over X. Do you see where this is going? And what about E over F? What's that? And through the magic of math, X divided by X is what we have here, right? Right, division's on the bottom, multiplication on the top. So what's X divided by X? 1. So that becomes 1. What's Z divided by Z? 1, right? What's Y divided by Y? 1. What's 1 times 1 times 1? So, by Ceva's theorem converse, we know that these segments must be concurrent. So I'm going to write AE, BF, CD, concurrent. So most of the work was done by our lemmas, right? To be able to get this guy, right? That theorem right there kind of unlocks the door for everything. And then our lemmas we learned earlier, like Ceva's theorem and all the other stuff, does most of the work. So the proofs we're doing after our lemmas and after these guys, right after we've proven this new theorem, they're not going to be that hard. Proving concurrency is actually pretty easy if you have the right tools to do it. How do you feel about that? We need to know what A over B times C over D times E over F is, and we need to prove that it equals 1 so we can use this to win, right? So I found out what A over B equals. It's X over Y, right? Et cetera, et cetera. Yeah?
Can you explain like how we knew all those equal each other?
Mm-hmm. Yeah, I think that's the hardest part.
F line?
Yeah, I think that's the hardest part of this. So if you look, this is CD, right? Does everybody see that? That this is the same as CD. I'm just drawing the diagram down here. So this is CD. What are the sides of our triangle? X and Y. And what are the bases? A and B. And we know by triangle angle bisector theorem that if this is an angle bisector, then the sides of the angle will be proportional to the bases, right? Remember that from the thing we just did last page, right? Now I did that for all of these angle bisectors. So if I turn the triangle, maybe it'll help. Maybe it won't because the letters are all upside down now. But look, the sides here are X and Z, right? And the bases are C and D. So Z over X equals C over D. With me? All right, same thing for the blue. Because that's an angle bisector by triangle angle bisector theorem, Y over Z will equal E over F. Are you with me on that? We feeling better about that, Jericho? Okay. Taylor, you with me? Okay. How about everybody over here? Nolan? Right. And that's it. Because once you have that, you win, basically, right? How do we feel about this? Decent, okay. Maybe not 100%, but like doable. Okay. The real key is understanding this theorem, right? Are you going to have to prove this theorem on the quiz? Oh, yeah. Oh, yeah, you will. But right after you're done proving it, you can use it. We're moving quick. So here's the theorem, right? Triangle angle bisector theorem. If that's an angle bisector, the sides go with the bases. So we did it. We proved our first Cevian concurrent. We'll try it. I'm gonna go grab some paper and I'll pass it out to you. I think the thing that's in there I wanna. Yep, I do. We're going to prove that medians are concurrent. And this is actually one of the easier proofs. Throw this over here. So we'll end on an easier proof. Okay, and these are double sided. Yep. Add this onto your packet. Here's page 9, 10, and 11.
Can we pass the stapler around?
Yes. There you go.
Then I've read essays, so.
You got one ready, Dylan? Alrighty. So let's prove that medians are concurrent. Now, what is a median? Right? They tell you that these are medians. What does that mean? G will be the center of mass, right? Now, we don't know. We're trying to prove that medians are concurrent, so I'm assuming that G exists there.
2-to-1 ratio.
2-to-1 ratio. What else do we know about medians? Center of mass. What's the definition of a median?
Vertex.
Vertex to midpoint. Very good. So we know that if that's the vertex, what must E be?
Oh, I already had it.
Midpoint, right? So we know by definition, which we're going to get for free, that these are concurrent. Now, if AF is a median, then that means that BF and FC must be congruent, right? Because F would be a midpoint. And then same dumb crap for this. I will use purple. Bailey needs all the help she can get. Her cat destroyed her paper. It is pretty. So we know that, right? So how are we going to prove that G is the center of, right, it's where they all intersect, that these guys are concurrent? Well, in order to prove something concurrent, we basically have to use Ceva's theorem's converse, right? So we need to prove that these guys over these guys over these guys equal 1, right? So, who can do it? We need to prove that this over this times this over this times this over this equals 1. And once we have that, we basically win.
Shouldn't any
You can do this. What?
medians should create a medicenter?
Right. We're proving that the medicenter exists, basically. Right? We know it does. We know it does, but we're proving it exists, right? We showed it on GeoGebra that it always stays, right? They always intersect, but we're proving that without having used GeoGebra. And this is good because this is actually a really easy proof and you want to get free points on your quiz.
Wait, what?
This is actually a really easy proof. How do we prove that this divided by this times this divided by this times this divided by this equals 1?
We
We
can
need
draw
to
a
make the
lowercase
triangles.
You could if you want. What?
We need to make the triangles similar.
Thinking too hard. Much easier. You want to add in little letters?
Yes.
Right, let's write let. What do you want to call this little guy?
F. B.
A.
Not in a circle without that.
Now, what do you want to call this one?
B.
Why?
Because A, B, C.
Well, aren't they equal?
Call them both A.
Call them both A.
Oh, yeah, I guess.
So we're going to say let AE, AE, capitals, equal A. Let BE equal A. You don't have to do this, but you guys wanted to write little letters, so we'll do it. And then we're going to let BF and FC, or let's do CF. What are we going to call them?
B.
Little b.
B.
Thank you. And let CD and AD equal what?
No, we do something stupid like
Oh, no, I just see.
No.
D.
No, I
We
refuse.
skip the C.
So,
Just mark it on the diagram, please.
we need to prove that these segments here, right? Yes, I can.
Thank you.
All multiply to 1, right? So let's do AE over BE times BF over FC. Do you see how I'm just grabbing these sides, right? I'm setting up Ceva's theorem. CD AC. Now we can't say that equals 1, but we do know what it equals. What do AE and BE equal?
A.
A, right? And what do BF and CF equal?
B. Oh my god,
And what do CD and AC equal?
C.
Which implies 1, right?
How would you do
Right?
that?
A divided by A. You would say that AE equals BE. You'd set AE equal to BE. And so when you'd substitute, you'd write AE over AE, BF over BF, and CD over CD.
I think I just like the letter.
Little letters is fine. So, by Ceva's theorem's converse, we know that AF, BD, and CE are what? Ceva's theorem's converse, right? If we know that they all multiply the sides of the triangles that we made.
They're concurrent.
They're concurrent, yep. How do you like that proof?
I don't like it.
Medians are always concurrent, right? Because when you multiply these pieces together in division, and divide these and multiply, and divide these and multiply, of course you're going to get 1, right? Because they're all the same. A divided by A is 1, B divided by B is 1, C divided by C is 1. So when you multiply them, of course you're going to get 1. Very easy proof.
I don't know how you can say that those all equal 1.
Well, we know that these are the same, right?
Yeah.
So we can call them the same variable. Is that cool?
Yeah.
Right? Same thing here and same thing here. So when I multiply AE over BE, right, and BF over CF, and CD over AD, what I'm really doing is multiplying A over A, and B over B, and C over C. What's any number divided by itself? What's any number divided by itself? Right, do you see it now? Yep. That's fun, isn't it? Much easier than the last one. The last one we had to use angle bisector theorem.
Wait, does that work for any median?
Yeah, right? Think about it. Draw any triangle, and its medians. Don't you get this? A, B, B, C, C. Then you set it up, and you get Ceva's theorem, right? And if Ceva's theorem's true, then by the converse, they're concurrent. Right? We didn't start out with anything special in this diagram. I just drew a random triangle and told you those were medians. You do with any triangle. Feeling okay? So we've proven that angle bisectors are always concurrent and medians are always concurrent. Tomorrow, we're going to get to perpendicular bisectors and orthogonals, right? That's going to be much more involved. We're going to have to learn one more theorem. Perpendicular bisectors is not that hard. Orthogonals, to prove that they're concurrent, is pretty involved. We're going to draw some pretty crazy diagrams. It's going to be fun, I think. And it kind of flows. If you know perpendicular bisectors are concurrent, then orthogonals
Can I
must be.
have those papers?
The extras? The new page?
Like,
Oh, the ones I did just now? Yeah, you can have.
When you're, not
Not yet. I'm gonna give it to you at the end of the week.
About how I broke my hand. Your actually, I didn't break it.
You wanna hear the story of how I broke your face?
Whoa.
So,
Looks like a true story.
it is. Let's talk about my hand first, though. So, I was at the top of my pool, and the floor was slippery in the locker room. And so, I got dressed on the bench, because I didn't want to get my feet wet.
She was standing on
And
the
so,
bench.
I was standing on the bench, and I stepped off, and I literally slipped and fell. And hit my
All right,
face
nerds, so
hard.
The plan is to prove concurrency for our other two angle bisectors and orthogonals tomorrow. And then on Wednesday, we're going to get into doing math with this stuff. So basically, like, if I were to give you a triangle, I'll see you later. Super easy stuff. Basic calculus. And then we're finally done with this stuff, and we're going to go on to doing trigonometry. Trig is cool looking. It looks intimidating, but it's actually one of the easier
Don't
things to do.
throw
all
those
year.
away. I'm hanging them on the back wall tomorrow.
Ooh, nice, nice.